Hi, welcome to Coding Bootcamp's YouTube channel. Subscribe now and join our live stream session later. See you.
Hello, welcome to project number 1 in our Intro to C Programming course. So, what this is going to be is I am going to go through as slow as I can, and I'm going to show a solution to the problem in the first project. Hopefully, by the time you're watching this, you will have done it yourself and will have gotten it working as best as you can. If you haven't done that, no worries, we'll run through it together, and the source code for this will be available on the site for you to read yourself. If you have already done it, then what you can do is you can compare your source code to mine, see if we did anything differently, and if we did, see if you can figure out why that is. My code isn't necessarily better than yours, it might just be different. And as long as it works and does so in an efficient manner, the small differences really don't matter, do they? So, before I get started here, let's determine what the problem we're doing is. So, I've written 3 steps up here. First thing we're going to do is we're going to get input from the user in the form of an integer. Check if the int we get is positive or negative, and print out a message according to the results. I've also done one more thing to get prepared. I have our entry point function, int main, that takes void and returns 0. This is the only function that is necessary in every C program, because what the compiler will do is when it compiles our file, it will look for a function named void, or named main, and if it finds one, it's going to say, okay, I'm going to start the program there. If it doesn't find one, it's going to get very confused and then be sad. And, put errors at us too. That's kind of important. So, let's get started here. What are we going to do? We don't have any files included here, so we don't have access to any standard library functions. So let's get started with that. We're going to need printf, and we're going to need scanf. So, pound include, so this is telling the preprocessor that the file that I'm going to give it next, so stdio.h, this include tells the preprocessor that it's going to find this file and copy paste it into my source code file, starting at this line right here. Next up, we're going to need one more thing, I think. No, actually, I think this will be it. Let's see, I may have been thinking of a different solution to this problem. So, let's see what we got here. First thing we're going to do is we need to ask the user for input. So let's do that by giving them a message. Printf, printf. And what printf does is we will give it a format string, is what it's called. So we're going to say input an integer. Do the /n there. And so, printf expects a format string, or a constant character pointer, or just a string. So in C, we surround string literals, that is, things that are not meant to be interpreted as code, but just meant to be interpreted as this particular string of letters and characters. We surround those in double quotes. Here, we're just asking the user to input an integer and have a /n at the end. What that is it's called a new line character. And what that will do is when we do this, when we run this on the terminal, instead of just continuing this line afterward, it is going to start a whole new line. That was wrong. It'll start a whole new line for the user to start typing on. So now we've got that. Next up, we're going to be getting the integer from the user. So we'll scanf, scanf. Scanf can be thought of as kind of the opposite of printf, in that instead of giving scanf a format string to output, you give it a format string of what kind of input it needs to look for from the keyboard. So we're going to be doing that here. We have another string here But instead of having anything that's human readable, we're just going to have a percent and then a lowercase d here. And what that does is it tells scanf to look for a decimal number or an integer. Next thing scanf expects is somewhere to store the data it gets. We don't have that yet, so let's go up a couple lines and let's do that. Let's call it int input 0. We're initializing this because if the user fails to input something that we expect them to, we'll just default to 0. And now we need to tell scanf that it can store its results in input. So how do we do that? We're going to pass a pointer to input. So we're going to use the address of operator here, input. And so what this will do is it will give the location that input represents in memory to scanf. And what scanf will do is it will scan the line we type in on the keyboard for an integer to put in. And if it finds one, which we're assuming it will put that integer into the memory that input represents. So now that we've got that, let's keep going. Next up, we need to determine if the integer we get is positive or negative. So we're going to do that using two comparisons. And a few if-else blocks. So here's what we do. Say if, and what we're going to do is, the first thing we're going to do is we're going to check if input is less than 0. So if input less than 0, have our curly braces here for the actual result of the statement. And so what this is doing is if the number loaded into input right now is less than 0, then this whole expression will evaluate to the number 1. As we know, with Boolean expressions, 0 is false and 1 or anything that isn't a 0 is true. So if we get a true here, we execute all of the code in here. But what if input is greater than 0 or equal to 0? Well then, else if input greater than 0. And now we have that situation covered. And if input is not less than 0 and it's not greater than 0, we don't need a third check. At this point, we know it's 0. So, last we just need an else. And now we're going to fill in these blanks we left here. So what do we do if the input is less than 0? Well, we'll just tell the user that much. Printf %d is less, it's negative. And then I need the input. Yep, there we go. So just to go into excruciating detail here, we have printf again. We've seen that up here. This time we're giving it an actual format string instead of just a regular string to output. So we have %d is negative. That %d is going to be replaced with the value of input converted to a string. So whatever is in input, it's going to get put back out onto the screen, followed by is negative, and then a line break. Else, if input is greater than 0, well, we just need to do something similar there. Printf %d is positive. Put else. This is our last case here, so this will only fire if input is equal to 0. So printf 0 is neither positive nor negative. And there we go. This should work. Let's find out. Let's see here. I'm going to clear. What did I name this? Project 1.c. Okay, cool. This is, I'm pretty familiar with operating on a terminal. You don't necessarily have to, especially if you're using an IDE like Visual Studio. If you're curious, this ls just lists every file in my current directory, which right now I have it set to where I'm storing this file. So let's clear that again. GCC project 1.c. It would help if I could type -o project 1.exe. The compiler didn't say anything, which means everything is working just fine. For programs like GCC, getting no output is a good thing. That means whatever it did it successfully and quietly. So now we're just going to run project 1.exe. Please input an integer. Cool, that's about what we expected. Let's start with 5. 5 is positive. Good to know. We're going to try this again. This time I'm going to try -78. -78 is negative. One more time with 0. That works the way we expect it to. And now, just for grins, we're going to try something weird. Let's say 999. And you'll see we ran up against the limit of the integer data type here, but other than that, it still works. So an integer can't store a value that's greater than this, but even under these circumstances, it still worked the way we expected it to. Last thing before I go is I'm going to try giving it something particularly weird. So, project C. Let's try giving it something that isn't even a number. Let's try just a random string of characters from my number pad. Cool. Under those circumstances, scanf fails to do anything of import, and then we just use the 0 that's loaded into input by default. Good to know. Cool. The source code that I've written here will be available on the website for you to study and play with and tinker with on your own time. Thank you for joining us. Hope you had fun doing this. Hello, and welcome to project number 2 of our Intro to C Programming series. Like last time, hopefully you'll have done the project already, and we'll have a working version of it, and you'll be able to use this video to see where we did things differently. If you haven't done it yet, or if you got stuck, no worries, feel free to follow along. By the end of this video, we will have a fully functioning version of the project, and we will, and I'll be explaining my thought process the whole time, so you'll be able to see how I'm doing things in real time. So, what's our goal for this time? Given 3 numbers, print out the greatest of the 3 of them. Specifically, we're going to get 3 integers, so not floating points and not characters or anything else. I've broken this down into a set of 3 steps before we get started here. Step 1 is going to be get the 3 numbers from the user. Step 2 is going to be sort the 3 numbers we are given. And step 3 is going to be output the result to the terminal. So, let's figure out what we're doing here. We already have standard io.h included, and that should be the only include we need for this. Oh, and you'll notice my text editor looks different this time. I've been using Notepad++ and the Windows terminal up until this point. For the next couple of projects, I'm going to use Visual Studio just to mix it up a little bit. Fundamentally speaking, there's not that much of a difference. Visual Studio being an IDE, or integrated development environment, will just do a lot of things for me, like compiling it and running it all at once, just using this green play button up here. Personally, I don't like to use that. I feel like it takes a little bit of control away from me, but it is a perfectly suitable tool for any programmer. Really, it comes down to a matter of personal preference, and that's what I intend to show here. So, let's get started here. So.
Thanks for watching. Feel free to add your questions as comments down below.
Step 1, seen above. So first thing we're going to do is we are going to get our 3 numbers. I want to store those 3 numbers all together instead of having them all separate. So I'm going to use an array. Int number, or numbers, let's pluralize that. Have that be an array of 3 of them, and if I can actually hit the correct keys, that would be nice. So now we have a collection of 3 integers. I actually want to initialize these. So let's have them all set to 0. Ah, right, that doesn't work. Okay. And so now this is where all of the data that we get from the user is going to be stored. So now we want to actually get the input from the user. In order to do this kind of all at once, or rather so that I don't have to write all 3 steps of it out individually, I'm going to use a for loop here. So, for int I equals 0, I less than 3, plus plus I. So let's see, I'm already noticing something. We use just a raw number 3 here and just a raw number 3 here. If we wanted this to be a little extensible so that we could get any number of input numbers, what I could do is I could define const int max or array size equals 3. And then what this would do is I could just plug array size in here and here, and then I would be able to get as many as I want, and all I would have to change is this one number here instead of both of these. I'm not going to do that right now, but that is an option if we wanted to use a larger array. Let's keep going here. So what we have here is a for loop. If you remember how these work, what this is going to do is this is going to run exactly once when we get to this line when the program is running. This is going to be checked every time the loop intends to run. If this evaluates to true, then everything in the loop will run. If this evaluates to false, then it's going to skip the loop and move on to the next line. And finally, this is going to be run at the end of every iteration of the loop. Just to get a good... Oh, that's my phone. Just to get a good idea of what's going on here, here's another way to write that. So let's say we have int I equals 0, while I less than 3, loop stuff here, plus I. And just to have every detail written out there, this is going to start at 0. 0 is less than 3, so everything will run in here. Then we're going to plus I. So I will be 1 at the end of the first iteration of the loop. 1 is less than 3, so it'll run again. Then I will be 2. 2 is less than 3. Everything will run a third time. And then I will be 3. 3 is not less than 3. 3 is in fact equal to 3. So the 4th time that this gets checked, the loop will be skipped and we'll be done with it. We'll be running the loop exactly 3 times, and that's what we want. Just for the sake of having... just for the sake of taking up less space on the screen, I'm going to be using the for loop syntax up here, but these are functionally identical. So, select all that, delete that, And let's get going here. So first thing we need to do, prompt the user for input. And the second thing is we need to get input from the keyboard. Or that's not strictly accurate. Let's get input from standard in. That is more accurate. So we need to use printf here. This prompt will be pretty familiar from last time. And the reason part of the reason I'm using a loop here at all is so that I can do something clever with the loop variable. You'll notice I'm using %d here, and that means that I'm going to pass printf an argument here, or I'm going to give it another variable to print out. In this case, I'm going to print out I plus 1. And what this will do is I can actually go ahead and run this. Yes, here we go. Can I zoom in here? Yes. And so you'll notice what this is doing. That means I typed it wrong. But what this is doing is this is input number 1, input number 2, input number 3. This will make our output nice and organized. That's what I did wrong. Put the period in the wrong place. So there. Now it should look the way we want it to. Let me run this again. Cool. Everything's good. Now, instead of just printing out that message, we want to actually, get something from the user. So let's do that. We're going to use scanf again. And so now scanf needs to know where to store the value it gets. So let's use that array we declared earlier on line number 18. This time, this is another time when we can use this loop variable I. So what we're going to do is we're going to say store it in the address of numbers element I. And so what this will do is the first time this loop runs, it will prompt the user for input number 1, that's 0 plus 1, and then it will store the value that the user types in numbers element 0, so kind of right here visually. Then the second time it runs, it will ask the user for number 2, and store that in numbers element 1. Remember, arrays start at 0. And then the third time it runs, it'll ask for number 3, and then store that in numbers element 2. And we'll, real quick, just for grins, let's make sure that works. For int I equals 0, I less than 3, plus I, printf number %d, %d, and we'll be giving it I plus 1, numbers sub I. If this is doing what we expect it to, then after we put all our numbers in, this will print then all the numbers back out. This isn't the end goal of the project, but it will be a good way to check that our thoughts are correct. So let me run this real quick. Build errors. What have I done wrong? Scanf function may be unsafe. Ah, right. Okay. So... okay, so this is Visual Studio trying to put a certain coding style on me. It is absolutely correct that scanf is technically not memory safe. Right this moment, I don't actually care, so let's see if I can make this go away. Define CRT secured no warnings. Maybe that will work. Yes, it did. Okay, so that's all it wanted. Please input number 1. Let's have it be 4. Number 2 will be 5. And number 3 will be 999, 999, 9999. Cool, that's about what we expected. Number 4. That's not quite right. What's going on there? Have I done something wrong? Ah, I see what I did wrong. I did I plus I instead of I plus 1. Small mistake. Quick little typo. Let's try this again. Let's see. Let's do 7, 8, and 99. Yes, this is what we expected, so everything is working according to how I said earlier. Good to know. Now we can throw this out and get back to what we were doing earlier. Step 2, sort the input. So we want to know which of the 3 numbers we got is the greatest one. Effectively, what that means is we have to sort them in such a way that the greatest one ends up where we expect it to. And under those circumstances, whatever is in that location is, by definition, the greatest one. This is something I'm going to be doing a couple of times, so instead of doing it in a loop, I'm actually going to break it out into a different function. So let's go up here. Let's say void swap. Int pointer left-hand side, int pointer right-hand side. Need a comma here. And so the way we're going to sort it is pretty easy. If number sub 0 is less than, or no, not less than, greater than numbers sub 1. We're going to swap those two. What this will do is if... let me run through this using... I'll just type out an example, and we'll see how this works. So let's suppose we have the numbers 55, 76, and 88. That's a terrible example because they're already sorted. 88, 55, 76. There we go. So here's what we're going to do. We're going to compare this 88 and this 55. 55, or rather 88 is greater than 55, so we're going to swap them. If I can get things to cooperate. There we go. So this is going to be 55, 88, 76. So now we know that 55 is in the correct spot. We don't necessarily know that 88 is in the correct spot, so let's check again. We're going to compare the 88 and the 76. 76 is less than 88, or rather 88 is greater than 76, so we're going to swap them again. 55, 76, 88. And now they are all sorted. And we know that the greatest number is in the last position. This is what we'll be doing here. So in fact, oh, that was loud. My apologies. My office chair is trying to kill me. Ah. Come on. There we go. And cut and paste that there. So now we have a comment that will explain the, this diagram shows the sorting algorithm we'll be using step by step. So, original first swap. If I could type, that'd be really helpful. There we go. And then second swap. And now this will be a kind of visual example. So let's write the code for that here.
If you have enjoyed watching this video, please subscribe to our YouTube channel. Thank you.
If numbers element 0 is greater than numbers element 1, we need to swap the two. We can't swap them by passing copies of them, so we couldn't swap them by doing this. This would just send copies of number sub 0 and number sub 1 off to swap, and then nothing would actually change in the array. So we need to send pointers. And now, when we send these two pointers off to swap, up here, swap is going to work on the original data and not copies of the data. We'll actually write the code for swap in just a moment here. But for now, just swap does exactly what it says. It takes whatever is in LHS and puts it in RHS, and whatever was originally in RHS will go into LHS. LHS and RHS are left-hand side and right-hand side, respectively. This is a shorthand I find myself using pretty often for functions that take two arguments like this. And particularly, I use that shorthand when there's no meaningful difference between the left-hand side and the right-hand side. So, for example, these two lines would be functionally identical. Swap at numbers sub 0 at numbers sub 1 is the exact same as swap numbers sub 1 at numbers sub 0. Because I don't have to differentiate them, I can just call them the left-hand side and the right-hand side, and everything makes perfect sense. So, that's our first swap. Then if numbers sub 1 greater than numbers sub 2, we're going to swap those two. There we go. You might have noticed, I have the memory of a goldfish. So, we have our swaps now, but the swap doesn't do anything. It's just a blank function. Let's go ahead and write that function right now. So, how do we want to do this? Well, if we try doing star LHS equals star right-hand side, then we lose whatever was originally in right-hand side. So we need to save that first. So let's say int temp for temporary equals star LHS. If you remember how pointers work, you can declare a pointer by adding a star after the data type, and what this means is this is more or less a reference to an int. It's not actually, it is not the int itself, it refers to where the int is stored in memory. Similarly, if you put the star in front of a variable that's already been declared, or in front of a pointer that's already been declared, then this dereferences the pointer. This turns the pointer back into the actual number, so we can actually get the value here. So, now we have the original value of left-hand side stored. Let's see, this line here moves the value of RHS into the value of LHS. And this line right here, well, I'll comment it after I write it. Star RHS equals temp. And so now we have used the value that we saved earlier. So use saved original value of LHS and move it to RHS. And so now, at the end of this quick little function here, whatever was originally in LHS will now be in RHS, and whatever was originally in RHS will now be in LHS. Easy. Step 2, sort the input. I should move that up here. And so, at the end of these swaps, the greatest number should be in numbers element 2. We can use that in our output message. So, as an output, we're going to printf %d is greater than %d and %d. So now printf is expecting 3 numbers because we use the %d 3 times. And we're going to give it the numbers from the array we have. So numbers sub 2, numbers sub 0, numbers sub 1. The semicolon is in the wrong place because I forgot how to type again. Get rid of some of these blank lines. Ignored return value from scanf. I don't care, that's not the point of scanf. Cool. So, let me zoom out a little bit. This is what I assume to be a finished version of the project. I will test it real quick, fix anything that needs to be fixed, and I'll upload the final source code to the website. So let's compile this. I'll just use this button up here. This is part of what makes IDEs like Visual Studio so easy. Instead of having to have the command line memorized like I've shown you in the lectures, you could just hit this button. Please input number 1. Let's do 99. Number 2, I'm gonna say 56. And number 3, let's do 67. 99 is greater than 56 and 67. Cool. That seems to be working the way we expect it to. I'm going to test this one more time. This time I'm going to put the numbers in the right order to start with and see if anything happens. So let's do 4, 5, and 6. 6 is greater than 4 and 5. Excellent. Everything seems to be working the way we expect it to. One last run through before we close this off. First thing we do, we declare an array of 3 integers. We get our input by using a for loop. This allows us to both organize our input, make things look a little nicer for the user, and it allows us to get all of our input at once instead of having to write these 2 lines out 3 times. Then, once we've gotten all of our input, we do a small little sort here. We just determine if the numbers are in the right order. So if the first number is greater than the second number, then they're in the wrong order. We swap them. If the second number and the third number are in the wrong order, we swap them. Easy as that. Finally, we output which of the numbers is greatest and return 0, exiting the program cleanly. Cool. Looks like we've gotten everything done here. Feel free to tinker with this source code yourself, and hope you had fun. Hello, welcome to project number 3 in our Intro to C programming course. Like usual, hopefully you'll have done the project already, but if you haven't, that's especially okay this time because our goal involves a kind of advanced C technique. This time you might want to follow along pretty closely. So, our goal this time around is we're going to be outputting the Fibonacci series to the terminal. We're going to be doing this in 2 different ways. The first is we're going to be using loops. That's just a regular iterative method of doing it. And the second is we're going to be using recursion. In C, and in C-like languages, a recursive function is a function that calls itself somewhere inside of it. These can be a little iffy if you're not careful about how you write them. They can call themselves in an infinite loop, and this can be a real pain to diagnose. If this, under some circumstances, if this happens, the memory that gets allocated to your process by the operating system will run out and you'll just crash. Sometimes it can loop infinitely. It's a mess when it happens. But for something as simple as this, it really shouldn't matter if we mess up and do that. Fixing it would only be a couple of keystrokes away. If you don't recall, the Fibonacci sequence is a mathematical series. Fibonacci sequence series? I don't remember which word is appropriate for this. I'll be using series. The Fibonacci series is a mathematical sequence of numbers generated by starting with the sequence 0, 1, and then every further element in the series is gotten by adding the previous two together. So the third elements in the series would be 1, then 2, then 3, 5, 8, 13, etc. Is my arithmetic right there? Yes, looks like it is. I'm bad at math. That's why we have computers to do it for us. So, what I'm going to do here is I'm not going to have two separate files for this. Instead, what I'm going to do is I'm going to have void Fibo iterative int num int terms. Let's do that. Int terms. And I'm also going to forward declare int Fibo recursive int term. And you'll see why I pluralized one and not the other here in a moment. And the goal of main here is going to be to determine how many terms we want, and to determine which method we want to use. The output should be the same, maybe give or take a couple of messages we put out to differentiate them. But I want to have this all in one file, because that makes it easier for me to do all in one video. So, let's break this down into steps here. Steps. Step 1, get number, if I could type, number of terms from the user. 2, get method from the user, either iterative or recursive. Number 3, run that method, outputting the terms to the screen. So, that is the brief version of what we'll be doing. By now, hopefully you've watched the other two videos or done the previous projects yourself. We should know how we're going to get input from the user. We're going to prompt them using printf, so printf input the number of Fibonacci terms you want to see. And we're going to use scanf again because... No, you know what? I said I put in the comments of my last source code file that I would show the memory safe way to get user input. So a hiccup we ran into last time. Let's see if I can replicate it here. We're gonna say int terms scanf %d address of terms. And if I'm correct, let me hit save here. Ignored return value, maybe that's not quite right. Let's try hitting that. There's what we wanted. It says down here, scanf, this function or variable may be unsafe. Consider using scanf_s instead, yada yada yada. What I did last time to disable this was I just did a pound define, that told the compiler to ignore those warnings. This time around, I'm actually going to do the memory safe thing. So the reason scanf is not memory safe is because when you
Thanks for watching. Please like and share this video.
pass it a pointer, you could be passing it a pointer to anything. And it can't possibly tell the difference between, say, an int pointer or a character pointer or a pointer to a string or a pointer to some other structure or even a pointer to a function. And so it's entirely possible that we could do something like this: char temp, and then we would say scanf, put a whole 4-byte integer into this 1-byte space here. You can't do it. What'll happen is it will try to load, it'll load the first byte into temp, and then the next 3 bytes are going to be next to temp in memory we don't have access to. If this happens in the wrong place in memory, our whole program will crash because we've gone into memory we're not supposed to. Bad idea. So here's what we're going to do instead. We are going to define an array of characters. We'll call it buffer. And I'm going to say have it as a 64-byte buffer. Remember, characters are 1 byte, so this whole buffer is just one 64-byte long chunk of memory. We are going to, instead of using scanf, we're going to use a function called fgetS. What fgetS does is it just gets an entire line of text up to max count. You can see it might be a little small on the screen. The second argument for fgetS is the maximum size of the buffer that you're passing in. And it'll get it from any file stream that you tell it to. So that can be from standard in, that can be from a file on the disk, that can be from some other device hooked up to your computer. So, let's do this. We're going to pass it buffer. Max count is 64. And we're going to get our input from standard in. Is that going to complain to me about that? I don't know. Let me save this. Try building it, see what happens. Cool, doesn't complain. Good to know. I'm not using keyboard shortcuts in this, in part because an extension I use, I had to disable it for this, and now my keyboard shortcuts are all kind of messed up. This is actually good for the purposes of the video, because it means I have to go through every step one at a time. Let's not put that there. So, if I want to save it, I have to go all the way up to File, hit the Save button. If I want to run it, I have to go all the way up, hit the Play button. Alright, so let's keep going here. Now we have a buffer full of characters. Int terms equals 0. How are we going to turn that character buffer into the number that we want? We're going to use a function called a to I. A to I stands for ASCII to integer. It just converts a string of ASCII characters into an integer to the best of its ability. If it sees anything that isn't a number in there, it's going to get confused and stop. If it sees a period in there, it thinks it's a floating point number and it might get confused. It'll just stop. Old C functions can be kind of finicky in that way, but they're very reliable when you use them the way they were intended. So, in order to do this, we're going to say terms equals a to I buffer. Identifier a to I is undefined. Give me just a moment here to Google something. Okay, we're back. I figured out why it didn't know what A2I was. It's because I forgot to include. A2I is not in standard IO.h. It is in standard lib.h. So, now we got that. A2i is defined. We're good to go. Let's keep going here. Next things we need are the we need to prompt for which method we're using. So printf, do you want to use the iterative method 0 or the recursive method 1? And so what we're going to do here is if the user inputs a 0, we're going to use the iterative method. If the user inputs a 1, or actually we're just going to say anything that isn't 0, we are going to we're going to use the recursive method. We could make sure that it was either a 0 or the 1, but that would honestly kind of waste our time and not be the point of the exercise here. So we still have buffer. Buffer is still perfectly usable, so we're going to fgetS buffer 64 standard in. Same thing as last time. It is going to get up to 64 characters from standard in. Actually, more accurately, it's going to get up to 63 characters from standard in. fgetS makes sure that the last character in the buffer it has room to be the null character at the end of a string. And just a quick refresher, strings in C are just strings of bytes, like any kind of byte, with a null character, or a byte that's all zeros at the end. As long as the whatever is reading a string doesn't find a byte that's all zeros, the string is considered to be unfinished. All right, let's get going here. Now we have buffer. Let's say int method equals 0. Method equals A2i buffer. And now we're going to do our last bit here. If method equals 0, then we're going to use the iterative method. So we're going to call, what was I called it up here? Fibo iterative terms. And if method equals 1, we're going to use the recursive method. I'll write the recursive method last. So, first thing we want to do, let's just go ahead and get the function for the iterative method out of the way. We already have declared it up here, so we can actually put it lower than main in the file. So, void fibo iterative int terms. What do we need for this? Well, we know that the first two terms are defined for us, so let's say int first equals 0, int second equals 1. Int current. I want a variable to keep track of what term we're on in the series. I think I'm just going to call that cur, short for current, equals 0. 0, 1. I'm going to say 0 will work for now, and if it turns out to be wrong, I'll switch it to 1. Typically, when you're counting in a program, you're going to start from 0 instead of starting from 1, because usually you determine when you've gotten to your goal using the less than operator, which means that 0 will be the first, and whatever your goal is minus 1 will be the last one. So, let's determine what I'm doing here. That's the wrong button. I've got something up on my second monitor right now to just check my own work here. Let's see here. We want to loop through up until the number terms. So let's just use a for loop for that. For cur equals 0, cur less than terms, plus plus cur. Let's see here. We know the first two terms, so we can actually kind of skip them. But we don't want to actually skip them because, well, we need to print out this series to the screen, and we're going to do that in this function instead of returning values one at a time, because that doesn't quite work for this. So how are we going to do that? Let's say if cur equals 0, printf %d new line character first, else if yeah, let's just do it like this. The minor overhead here isn't worth considering. So there is a slight performance downside to the way I'm doing this, and that's that cur will be checked against what's going to happen is these conditions will fire every time. I think I have a way around that though. If cur equals 1, printf %d /n second. And I think my way around that is doing this. If cur greater than or equal to 2. So here's what this is going to do. First time around, the first time this loop runs, it's going to run into this condition. It's going to say, well, no, cur is 0, so it's not greater than or equal to 2. It's going to go down here. Yes, cur is 0, and so it's going to printf this. Then it's going to skip this because it's behind an else, and go back to the top. Plus plus cur will fire. Cur will be 1 now. Cur is not greater than or equal to 2. So we're going to go here. Cur is not 0. We're going to go here. Cur is 1. We're going to print this. This ensures that these two conditions are checked as little as physically possible. That's kind of a micro optimization, but it makes me feel good to do it that way, so I am. The reality is checking these conditions takes less time than it takes to blink, so really it's an optimization for aesthetic purposes more than anything else. So let's actually get to this. We're gonna say int next term first plus second. Then we want to move, then we want to kind of shift those terms back because we're going to be using these later. So what we're going to do is first equals second, second equals next term. So let me see if I can explain what this is actually going to do here. When we start out, first is 0, second is 1. Another way to think of what these two variables represent is two elements previous and then 1 element previous. And so what this is doing is we're saying whatever was 1 element, or whatever was 2 elements back, we're going to set to what is currently 1 element back, and whatever is 1 element back, we're going to set to the current term. That way, the next time around, we will have the correct values in place. If we want to be extra sure that what we're doing is correct, when we output this, we can actually give ourselves a little bit of extra information. So,
thanks for watching. Feel free to add your questions as comments down below.
printf %d. Here's what I'll do. Yes. Okay, here's what I'll do. Printf %d term number %d colon space %d. And then the first number we're going to pass to printf is going to be cur plus 1. And then the second number we're going to pass is next term. Then at the very end of this for loop, we're going to printf one more thing. Put a space here because we didn't do that before. And this will help us format everything. Previous terms %d %d. First, second. So what this is going to do now is the first time this function runs, this check will fail, this check will succeed, so we'll printf 0. Then, before we go back to loop again, we will print previous terms first and second. In this case, it'll be 0 and 1. Second time this runs, it'll do the same thing, except this check will fail, this check will fail, this check will succeed, so we'll print 1, previous terms, 0, 1. Third time this loop runs through, this check will pass, so we will get 1 as a result of first plus second. First will become 1, second will become 1, and we're going to printf 1 as our term, and then we're going to get 1 and 1 for this. This might be a little confusing. Let me see if I can think this through real quick. If I... No, you know what? No, I think this is the best way to do this. So I'm actually just going to reword this. Currently held terms. This is more accurate. This will tell us which 2 terms of the sequence are actually being held in memory right now. And this will tell us whether we're doing things right. So just to make sure that I know what I'm doing, save this. I'm going to give this a quick test run. Assuming it compiles. It does compile. Let's zoom in here for real quick. I want the first 5 terms using the iterative method. I forgot to add a new line character. Try that again. Uh, 5, 0. Cool. That looks like what we wanted. Cool. Yes, I believe I'm doing this right. Just to check one more time, I'm going to do the first 10 terms. 10, 0. So 0, 1, 1, 2, 3, 5, 8, 13, 21, 34. That looks correct to me. And all of the values that are being held in memory look to be the ones we expected them to be. So, cool. I am going to say this is working. Let me remove these new line characters. Actually, no, I want these. Because now that I know that this is working correctly, I don't need this printf statement anymore. I do want this term number %d, and I want term number %d, cur plus 1, cur plus 1. Test this one more time. 10, 0. What have I done wrong? I didn't have the new line character again. So you can see what happens when I don't put that new line character in, is the line just never stops. And so I have all of my things on one line here, and it's the ugliest thing in the world to read. Let me fix that. But I know that this fix will work because I saw what I did wrong. So, the iterative one now works to our expectations. To run through this real quick before I move on to the recursive one, we know the first two values of the sequence. They are part of the definition of the sequence. And this value cur here represents which term we are on in terms of how many we're trying to output to the screen. So we have a for loop here for cur equals 0 less than terms. If we are beyond the predefined, if cur is greater than or equal to 2, if we have already output the first two terms to the screen, then we calculate the current term by taking the previous two that are held in memory using first and second. Then we shuffle around the values of first and second by essentially bumping each one back, or bumping each one forward a term in the sequence. And we output the value we calculated to the screen. If we are just outputting one of the two predefined ones, we do it like so. With that out of the way, it's time to actually do the recursive method. So how are we going to do this? We're going to start our new function here, int Fibo recursive. That's what I named it. That is, in fact, what I named it. Int term. So, like last time, the first two terms are predefined. The difference is, this time, instead of holding them as values in memory, we're going to... This function is going to calculate the term that is asked for on the fly every single time. This is going to be pretty slow, actually, compared to the above version, but it is a pretty easy way to demonstrate how recursion works. If you ever take an algorithm analysis course, you'll go into detail as to why this method of calculating the Fibonacci sequence is actually really slow. If term equals 0, or term... Ooh. That's a question. Let's consider that 0 the first term and not the 0th term. I'm doing this specifically... I have to come up with a standard for myself here, where if I mix up my definitions, if I say it's okay to ask for the 0th term in the Fibonacci sequence, counting it might get a little weird. So really this is kind of an arbitrary decision on my part. So let's say if term equals 1 or term equals 2, return term minus 1. So what this will do is if we ask for the first term, this will, this whole check will evaluate to true. If we're asking for the first term, this part of the check will fire, and we will return 0. So that's 1 minus 1 is 0. If we ask for the second term, we'll do the same thing, except we'll return 1. That's 2 minus 1. And specifically, this is what's called an exit condition. You'll notice this part of the recursive function doesn't call itself. It returns a definite value. So whenever we ask for the first or second term of the Fibonacci sequence, we don't have to keep calling ourselves to further calculate it. However, else return Fibo recursive term minus 1 plus Fibo recursive term minus 2. This is the fun part. So let's say for a moment that we ask for the 5th term in the Fibonacci sequence. So what we pass as term is 5. What's going to happen here is this check will fail the first time. So we'll go down here and we'll say, okay, return the 4th term of the Fibonacci sequence plus the 3rd term. Well, now we have to call our own function twice. So this time we're going to, for this part, we're getting the 4th term. So we're passing 4 here. These fail. In order to get the 4th term, I need to know the 3rd term and the 2nd term. Well, that's a bit rough, because now I have to do the same thing again. I need the 3rd term plus the 2nd term. And what this actually forms is a tree structure. So in order, let me see if I can draw it down here. In order to get the 5th term, let's see, let's do that here and here. I need the 4th term and the 3rd term. Can I put things in the right place? I guess not. That'll work. In order to get the 4th term, let's see here. Let's do that there and that there. I need the 3rd term and the 2nd term. The 2nd term is one of the terms I can just get, but for the 3rd term, I need... I'm so bad at drawing with ASCII. But for the 3rd term, I need the 2nd term and the 1st term. And you can kind of see how this keeps getting bigger as you ask for greater terms. And the issue with this is absolutely none of these terms are stored in memory. Every time I ask for the 3rd term, which you can see I'd be doing a lot, every time I ask for that 3rd term, it has to be recalculated all over again. That's kind of the inefficiency of doing it this way. But we have done it, and it's actually fairly elegant. So this function, unlike the iterative function, this function doesn't actually output anything to the screen. It just returns the number we ask for after thinking about it for a while. What we're going to do for output is do this. For int I equals 0, I less than terms plus I. Printf percent, let's see, term number %d, new line character. So same format string is down here. This time we're going to be doing I plus 1, Fibo recursive I plus 1. Because remember, down here we said that there is no 0th term. In fact, just to hammer that home, if term equals 0, I'm going to give it something ridiculous. Return minus 9999. Do not ask for the 0th term. So in this implementation, we define the first term of the series as 1, and the second term of the series as term number 2, as opposed to defining them as term number 0 and term number 1. Which means, since we're starting from 0 here, we have to add.
If you have enjoyed watching this video, please subscribe to our YouTube channel. Thank you.
1 to I whenever we use it. If I really wanted to, what I could do is instead this. So say start I from 1 and then use I less or equal to terms. Actually, I think that is what I'm going to do. I like reading that better now that I look at it. And it matches up with what we defined earlier. So now let's test that and see if it actually does what we expect. So let's get the first 20 term. Not 20. 20's a lot. Zoom in here so you can see. I'm going to get the first 12 terms. And I'm going to use the recursive method, so I'm going to type in 1. Let's see. 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89. All of that looks correct to me. So I think this passes our test. Cool. So, hopefully this has been informative to you. I know I kind of trailed off a few times and went in weird directions trying to figure out how I wanted to format the output, but this is a pretty accurate representation of my thought process over the course of writing this. Yeah, thank you for watching. Feel free to tinker with this code yourself, and I hope you had fun. Hello, and welcome to project number 4 in our Intro to C Programming course. This time around, you can see I'm back in Notepad++, and what is our project this time around? Given a number from the user, we're going to check if it is even or odd using 2 different methods. First method we're going to be using is the modulo operator. If you recall, the modulo operator is similar to the integer division operator, except instead of returning the quotient of the division, it returns the remainder. And method number 2 is we're going to be using the bitwise AND operator. I have a long comment down here that will explain how that all works when we get to that. Broken it down into a few steps again. Get process user input. We're pretty familiar with that by now. Passing the value to the relevant function, which kind of splits off into 2 things here. Instead of making 2 separate programs, like the last time I did something like this, I think it was last project actually, I'm just going to have 2 different functions, and we're going to ask the user which one they want to use. Method number 1 is we're going to use the remainder of the value divided by 2 to get the result. And method number 2 is we're going to check if the ones bit of the value is set to get the result, and I misspelled value. Okay, fix that. And lastly, after we do whichever one of these 2 methods we need, we're going to print a message to the user containing the result. So, pretty similar to other things we've done, so let's get started here. If my chair would stop trying to kill me. There we go. So, first thing we need, if we're going to have those 2 separate functions, we should go ahead and declare them. So let's have int is odd mod, and this function is going to take 1 argument. It's going to be called int val, and then we're going to have a similar declaration here, int is odd and it's going to take a similar argument. Cool. We will define these functions properly later. This is just declaring them so that later down in the file we can have them down there and everything won't be in the way. Int main. As you can see up top here, I've already included standard io.h. So let's get to work here. At this point, we should be pretty familiar with prompting the user for input and for processing that input from the user. I'm going to use the fgetS method again because I just personally prefer that one. So let's get started here. Printf, string, please enter a number to test the oddness of. Have a new line character there so everything doesn't get really ugly. Then let's declare our buffer here. So character array buffer. Let's have it be 64 bytes. Initialize everything to 0 to make sure nothing goes wrong. Let's see. I need fgetS. We're going to, the buffer is buffer. The number of bytes in it is 64. And the file stream is standard in. I need int value 0. Value equals a2i from buffer. And if you remember from last time, a2i is not in standard.io.h. a2i is in include standard lib.h. Cool. Again, from last time, this should be pretty familiar, but I'll run through it again in case you didn't watch or skipped or just forgot. So what this does is we have an array of 64 bytes. They're all set to 0. fgetS will get a line. Of input from standard in, so just from the keyboard input to the terminal. It will load whatever it gets into buffer up to 63 bytes. That last byte, if it needs to use it, will be guaranteed to be the null bit or null byte at the end of the string. Then we have int value equals 0, and we're going to load into value whatever number we typed in to into the terminal. If we didn't type a number, a2i will give up and return 0. So, that should be pretty familiar to us by now, and we're going to do something similar here in a moment. So printf, helps if I type it correctly. Would you like to test using the mod operator % or the AND operator? That key, there we go, ampersand. So this is going to be a little different from the last time I did this, in that instead of getting a number, I'm going to expect one particular character in the output, or in the input. So instead of we don't have a reasonable default here. We're just asking for one of these two characters, and anything else, well, we don't know what the user wants. So let's do this in a more robust way. If the user doesn't do what we ask for, what we need to do is ask again and tell them they did something wrong. So we're going to keep this line here, but we're probably going to move it in a moment. And I also should have a question mark and a new line character there. So how do we do this? We want to ask the user once, and if we don't get something we expect, ask again. Probably the best way to do this is a do while loop. So let's get that structure going. Do while something. What is that something? We need a character. So, well, we already have buffer, so we can just reuse that because now that we have value stored, we don't need whatever's in buffer anymore. So let's just use that. So we're going to do whatever we do in this loop while buffer sub 0, so the first character in buffer, is not equal to the percent character, and buffer sub 0 is not equal to the AND symbol. And that should work. So just to clarify what's going on here, and I'll delete that extra trailing space. So here's what's happening here. We have two separate Boolean tests that we're joining together. So how do we determine if this is true? If the first character of the buffer is not the ampersand, then this bit evaluates to true. If the first character of the buffer is not the ampersand? I said that wrong. My apologies. Let me back up. If the first character of the buffer is not the percent sign, this bit evaluates to true. If the first character of the buffer is not the ampersand, that's correct this time, this bit evaluates to true. If both of these other conditions are true, then this whole ordeal, joined together by this double ampersand symbol, will evaluate to true. If this whole thing evaluates to true, then the condition for looping is met, and we will jump back up to the top of the loop after we check it. I think this works. This probably isn't the way I would have written this if I wasn't just doing it all at once. Let me try to rewrite this in a way that makes more sense to myself. So if it is not the case that buffer sub 0 is the first symbol, or is the percent symbol, or buffer sub 0 is the ampersand. If I could find the right key. There we go. I can never remember the order those are laid out in. This makes a bit more sense for me to read. So while these are semantically the same, I find this easier to read because what it does is it checks. This check will be true if the first character is a percent. This check will be true if the first character is the ampersand, and this double pipe symbol here will make this whole bit true if either one of the conditions is true. And then this bang here just checks that it is not the case that this is true. What this means is there are fewer knots floating around in here. So I think what I'm going to do is I'm going to delete this bit, copy that line, paste that there, and I will write a comment to myself right below it, because the while needs to be on the same line as this, if I recall correctly. So do stop the loop if the first char of buffer is percent or ampersand. That explains it pretty well. Cool, and now you've seen the thought process behind defining conditions like this. Not only do you need to define it in such a way that that the computer understands it, but that you can understand it. Another way to go about that is to write out an entire truth table. So given the inputs, so is the first character of buffer the percent, is the first character of the buffer the and then you run through all of the logic yourself and write out all the results to make sure that you're actually getting the result that you want. I kind of did.
Thanks for watching. Please like and share this video.
I didn't do that. I kind of did it in my head while explaining it out loud as best as I could. So, let's get into what we're actually going to do in the loop. First thing we're going to do is we're going to do the user input prompt. So let's do that. Copy that, paste that line. That's where we wanted it. And we're going to delete that line. Cool, so now the prompt for input is part of the loop and not outside of it. We're going to get s buffer 64 from standard in. And we are going to, now we need to check if, so now we're coming up against, we're coming up against an issue where I need to check the same thing twice. So maybe we can change what this is. Or, you know what? No, it just makes, it's easier to read if we just check the same thing twice. I'm not worried about being efficient here. So let's say if buffer sub, or let's use the same condition. Let's use the same condition. That way we, that way everything is internally consistent. So once again, if it is not the case that the first character of buffer is either the percent or the ampersand, we're going to run the code in this if statement. Printf, please put the proper character for the method want. Let's see, and just for clarification, character I didn't recognize, %C. And we're going to output the character that was in error when user does something bad. Cool. This should handle our input checking. Just to double check, I'm going to compile this. So gcc star.c out project4.exe. No output, that means it worked. Going to run it real quick. Let's just enter 65535. Huh. Okay, that's interesting. Oh, you know what? I know exactly what I did wrong there. Regardless, I want to check if this works, so I'm going to put in a $sign. Cool. Let's put in a rows or an @ character. Cool. And lastly, I'm going to put a % in, and it works just fine. Cool. Okay, so what did I do wrong there? If you noticed, the % in this bit of output here was not printed. That's because I forgot something. Printf, whenever it sees a %, it expects a format specifier, like say %d or %c that we use down here. And the way you work around that is you just have a double %. And this tells printf, no, I'm not giving you a format string, I'm actually giving you the % to print out. And just to clarify, %c as a format specifier says the next argument I pass you will be a single character that I need you to output to the screen. But other than that, I know that that fix will work. Actually, I'll just double check anyway. Let's go do that. 4, and cool. Now we get the output we expect. Excellent. So now it's time to determine which of our two functions that we're going to use. We have these two functions here. So, if buffer sub 0 equals %, that's the modulo operator, so we're going to use the modulo operator. Let's call... Yeah, let's call, we're going to be calling, God, what did I name that function? I have the memory of a goldfish. I will just do this. And this isn't all we're going to do here, but it makes a good, outline, and we will expand upon this, later. Then, else if buffer sub 0 equals ampersand. I named this value, so I'll go ahead and replace this with value. Value. Cool. Now, figuring out how we want to get our output done is probably the last thing we'll do with this. Right quick, I want to jump to the actually interesting part of this and write these two functions. So, I'm going to just copy their declarations, put them down here, and replace those semicolons for the forward declarations with the curly braces for their bodies. And so remember, up here we are just telling the compiler that these functions exist somewhere in the code and not to panic when we call them. And down here is where we actually tell the compiler, okay, this is what these functions actually do. So let's get to work here. How do we, so we're going to be using the modulo operator here. And modulo, the way we're going to test if the number we get is odd is we're going to try dividing it by 2 and see if there's a remainder. All even numbers are divisible by 2, and so the remainder will be 0. All odd numbers are not divisible by 2 evenly. The remainder will be 1. So, let's do this. There are a couple of ways we could do this. One way is to just have this function be one line long. Return val mod 2. And so, if value is even, this will return 0. If value is odd, this will return 1 instantly. We can be a little more verbose with that. We can say if val mod 2 equals 0, we return 0. If val mod 2 equals 1, return 1. That, and make that an else if. And this is more verbose, but it is semantically identical to this and does the calculation more times if it needs to. So I think I'm going to use the one-liner method for this because this is relatively easy to understand. At least I hope it is. If you're not understanding what this does, we go over the modulo operator in the lectures, and I encourage you to play around with the source code, rewatch the videos, do whatever it is that you need to do to form a model in your mind of what this operator does to the operands you give it. Now, this one is one I'm going to go into a lot more detail on, using the bitwise AND operator. So you can see I've written a long comment here. Consider what an int looks like in memory. Remember that memory doesn't hold the numbers themselves, it holds electrical signals representing ones and zeros. So everything in memory is just binary. So a int in memory is 4 bytes of 8 bits each, so that's 32 bits. For clarity in reading it, what I'm going to do is I'm going to have them be in 4-bit chunks, and I'm going to separate the bytes using a pipe character. Cool. So now we have our 4 bytes in memory. Any of these bits can be set, and but for smaller integers, usually we're just going to be looking at the first 2 bytes or maybe only the first byte. I have an example down here. Consider the binary numbers 11, 12, 13, and 14. This is what those numbers look like in binary. Notice how in the odd numbers, this rightmost bit is set. In the even numbers, so 12 and 14, the rightmost bit is not set. Quick crash course for binary. Binary is just another way to count. And in decimal, each digit in a number represents a power of 10. So in this number, 4,582, that 4 means multiply that 4 times 1,000, or 10 to the third. The 5 represents multiply that 5 by 100, or 10 squared, 10 to the second. 8 says multiply that 8 by 10, or 10 to the first, and that 2 says multiply that 2 times 1, or 10 to the 0th. Binary is the same way. Each binary digit, or that's what bit is short for, represents a power of 2. So 1011 says multiply this 1 by 8, that's 2 to the third. Then multiply 0 times 4, that's 2 to the second, so we're just going to ignore the 4's bit. Then multiply this 1 times 2, or 2 to the first, and then multiply this 1 by 1, 2 to the 0th. Remember, everything to the 0th power is 1. Well, every positive integer anyway. So, actually, no, that's true for all real numbers if I recall correctly. Anyway, sorry, math is weird. So, if we check the ones bit, we can tell if the number is odd, because every other bit is a power of 2, and therefore it's even. So the other bits would be 2, 4, 8. Then these bits are 16, 32, 64, and 128. After that, there's 256, 512, and 2 to the 10th is 1024. That's the biggest one I tend to have memorized at any given time. You could easily pull the other ones just by multiplying them by 2, but overall, usually if you're dealing with more than 2 to the 10th, you're just going to have a computer do it for you anyway. So, now that we have this understood, what do we do in order to check that that bit is set? Well, we know what 1 looks like as a binary number. 1 in decimal is equal to just 0001 in binary. Using the bitwise AND operator, we can get a number, we can get a value where all of the bits that are set in both the first and second operator, or operand, are set in the result. So, for example, let's say I have 0, 1, 1, 0, 0, 1, 1, and I'm going to bitwise AND this. There we go. With 0, 1, 0, 0, 0, 0, 0, 1. The output of this would be 0, 1, 0, 0, 0, 0, 0, 1.
Thanks for watching. Feel free to add your questions as comments down below.
You see how only the bits that are set in both values are set in the result, including this ones bit here. If we want to tell if the ones bit is set, all we have to do is do the bitwise AND with 1. Easy. So let's use the same thing we did up here, except return val and 1. That's fairly simple. So if, and this also conveniently returns a Boolean value. If value is odd, then the ones bit will be set and this will return 1. If value is even, then the ones bit is not set, this will return 0. They have 0 bits in common. And this can be used as a Boolean value in an if statement. So let's go back up and do that. How do we want to do this? Let's do it the easy way. Let's do it the easy way for one and the complicated but fun way for the other one. They'll produce the same results, but they'll just be in different syntaxes so that you can compare how they are different but do the same thing. So, let's see here. Let's get rid of this, put this whole thing in an if statement here. So, if this is odd, printf %d odd character, pass it value. Else, printf %d is even. So that's the really easy way to do this. Now I'm going to do the kind of weird way. I'm going to use the conditional operator because I find that fun. If you remember what the conditional operator does, first you have a condition and then a question mark. And then if true, colon, if false. And these can be lines of code, they can be values. This whole thing is an expression that holds some value when evaluated. And so what we can do is printf %d is %s. Have the exclamation mark and the new line character. And then this %d means we're going to be getting value, passing it an integer. This %s means we're going to be passing printf a string to print out. How are we going to get that string? Well, first argument is obviously value. Second argument is, what did I call that? Is, odd, and for value. Then a question mark. If value is odd, we want to give it the string odd. If value is even, we want to give it the string even. And that's just an example of how you can use that conditional or ternary operator. So now that we have this, let's save our work. I closed my terminal because I am not very bright. That's also not quite what I wanted. That. Oh, now IntelliJ is going to open. That's not good. Thankfully, it opened on my other monitor, so I can just close it and not worry about it. Cool. So let me zoom in here. ANSI C, bash. ANSI star.c -o project4.exe. Cool. Project 4. Let's start with 7. I want to test using the mod operator. 7 is odd. The same thing. I'm going to test using the AND operator. 7 is odd. Let's do the same thing, except we're going to use an even number this time. 8. 8 is even. And then back up here. 8. 8 is even. Excellent. One last test of the input sanitization. So let's do 2315. And I'm going to put just the number 0. Cool. Didn't recognize that, so it does the thing we expect. Excellent. So, as always, this source code will be available on the website. I encourage you to play around with it, compare it to your own code, and see if you can figure out why we did things differently. My code is not necessarily better than yours, it's just different. And I hope you had fun with this. Hello, and welcome to project number 5 in our Intro to C Programming. Let's see here. Quickly, let's go over the goal for this one. Given n numbers from the user, n is also user-defined, we're going to sort them and print the sorted list. So, this is a bit more complicated than ones we've done previously. I know that in one of the earlier projects, I used a kind of abbreviated sorting algorithm for just an array of 3 numbers, but this time we're going to be sorting any number of numbers. So we're going to have to deal with that. We're not going to be using any complicated sorting algorithms. It's going to operate very similarly to the one we used last time, but I'm going to be going into more detail. The name of that algorithm is called the bubble sort. It's named so because the greater values will bubble up to the top. They'll just kind of float there to the end of the array. So, steps, pretty similar to usual. Get processor input, pass the array to the sorting function, so we're going to be breaking off into a function. Sorting function will return the array sorted in place, so we're not going to get a new array, it's just going to be the same array as last time, just sorted now. And then we're going to output the sorted list to the screen. So, real quick, we can predict that we're going to need the sorting function. And I want to have a helper function that will print the sorted list out to the screen. So let's do that right now. Let's see. The sorting function is going to be a void bubble sort. Takes an int pointer array, int count, and the array printing is going to be void print array int star array int count. That's not what I wanted to do. My apologies. This is the source code from the last one. I accidentally closed the project. Okay, here we go. We're back. Let's get to work here. So first thing we're going to need to do is we're going to need to process our input. I'll explain that sorting algorithm as best I can when we get to it. So, printf, how many numbers do you want to sort? Char buffer 4. Same as usual, I'm going to be using fgetS and a2i. So, standard lib.h. This is for to I. Cool. I'm kind of going a little quicker here because we've done this in basically every project so far. So I am trying not to waste your time here. F get S, buffer, 64 characters from standard in. Int num elements equals 0. 8 num elements to I. Buffer. Cool. There is a bit of a caveat here. If we get 0, or if we get something we don't recognize for the array size, then we're gonna have a problem. We can handle this in one of two ways. We can either repeatedly ask the user for input, or we can print an error message and stop the program. This time I'm going to print the error message and stop the program. So if num elements equals 0, printf cannot have an array with 0 elements. New line, return -1. I'm returning -1 instead of 0 to indicate that something has gone wrong. This is just a convention with main. Similarly, return 0 is convention that means everything went according to plan. Part of this is because of the Unix and Linux philosophy. We've seen with GCC that if GCC doesn't output anything, it means it compiled without issue. Similarly, other programs in that kind of space follow the same philosophy, and if they output anything, it means something has gone wrong. We're going to follow the same convention here. So, we don't need an else here because if num elements is 0, we're going to return -1 and the program will end right there. So what next? Well, now we need an int array with however many elements num elements is. So this is a variable sized array. Or more accurately, it is an array that has as many spaces as this variable evaluates to. You can't change the size of the array, you can just declare it differently. So now, we can't initialize this because the C runtime won't let us do that. So now what we have to do is we need to get all of the numbers from the user. So we're going to do that. We're going to use a for loop, or I equals 0. I want to put a few blank lines here so I can put this in the center of the screen where I can actually see it and it's not blocked by my microphone. So for int I equals 0, I less than num elements plus I. So what this will do is this will run this loop num elements times. We've seen for loops before. Hopefully you have played around with them a bit. Yeah, I don't see a strong need to go further into them here. Don't want to repeat myself too much. These videos get pretty long as it is because you're seeing my live thought process as I do this. So, I equals 0, I less than num elements plus I. Cool. Printf. So this time we want to prompt the user for input. We want to do it in a kind of clean way. I have an idea for this. What we're going to do is we're going to give printf a number and then a colon, and then we're not going to have a new line character. Instead, what's going to happen is the user will put the number in on that same line. And so what this is going to do is this is going to count first element, second element, third element, fourth element, and so forth. So, it's 1 because we want to start, we want to follow human counting conventions and not computer counting conventions. That was loud. And now we're going to get s, buffer 64.
If you have enjoyed watching this video, please subscribe to our YouTube channel. Thank you.
Standard in. Int value equals 0. No, A2I will return 0 if it doesn't recognize it. So what I can do is I can skip a step here and say array sub I equals A2I buffer. That will work just fine. And so this will run once for every element, and once it does that, the array will be full, and we can pass it off to the bubble sort function. So here, bubble sort array num elements. That is a colon and not a semicolon. There we go. Fix that. And now is a decent time to implement the bubble sort function. Actually, I lied. I can just call print array here. Now we're done with main. Now everything that we need from main has been accomplished. Cool. Now we can start properly defining these functions. So get their function signatures, copy them, go down here, and put those down. Now, so bubble sort. Let me draw a diagram as best I can here. Bubble sort will take in an array of unsorted values. What it's going to do is it is going to look at one value at a time. So let's put a star there. And let me double check. I've got the algorithm itself on my second monitor here, so I can double check my work. Yes. So what it's going to do is it is going to look at one value at a time, and then for every other value, it's going to see if it needs to swap the position of those two. So, for example, what it's going to do is we're going to start looking at this 4, then we're going to check the 7. 4 is less than 7, so there's no need to swap them. 4 is less than 9, no need to swap them. 4 is greater than 1, we do need to swap these. So we'll swap this, and then this. We're still looking at this position, though. So we're not looking at the 4 anymore, now we're looking at the 1 that we just put here. 1 is less than 2, stays. 1 is less than 3, stays. This second element here will provide a better example of just how many swaps can go on. So now we're looking at the 7. 9 is less than 7, this stays. 7 is greater than 4, so we swap them. 7, 4, cool. 2 is less than 2 is less than 4, so we swap them. And then 2 is less than 3, these stay in place. And I'll just quickly run through all of these because this won't take very long at all. So 9 is greater than 7, we'll just swap these. If I can remember how to type, that'd be very useful. 7 is greater than 4, we'll swap these. 4 is greater than 3, we'll swap these. And you can see how this 9 and 7 pair here has kind of bubbled up from here to this position here. And the 1, 2, and 3 are now in place. Let's see here. Have the 9, we swap it with the 7. 7 and 9. And then we swap the 7 and the 4. And then finally, we swap the 9 and the 7. And these. And now our original array, which I actually don't remember the order of right now, well, now it's sorted. And you saw me sort it right in front of you. Cool. So now let's actually write that as code. So let's write this as words and then as code. For each position in the array, for each position in front of the first position, so let's actually name these positions. For each position I and for each position k, such that k is greater than I, if the value of I, so if array sub I is greater than array sub k, swap array sub I and array sub k. Cool. We've got some pseudocode written here. Let's translate that into C. We're gonna need have our array, our count. We're gonna need a nested set of for loops here, I think. Yeah, so we have, well, yeah, we're gonna need those nested for loops. We have the for each here. If you can describe something using using terminology like for each, you should be thinking I'm gonna be using a for loop here. So for int I equals 0, I less than count, plus I. For int k, there I should be consistent, int k equals I plus 1, k less than count, plus k. Shouldn't have those semicolons there either. So cool, now we have a nested set of for loops. You can see that in the scope of the original for loop, we can use I as part of the definition for k. And what k is will change as I changes. So now we can, most of the work is going to be done in this second for loop. In fact, all of the work is going to be done here. So we know what we need to do in this second loop. If array sub I is greater than array sub k, we're going to swap them. If array sub I greater than array sub k, how do we swap them? Well, we did it last time. Last time I broke it out into a separate function. This time I'm going to keep these 3 lines all together here. So int temp equals not number, array sub I, array sub I equals array sub k, array sub k equals temp. Quick recap of what this is doing. We are temporarily storing the value of I in this temp variable here. Then we load whatever is in k into the space array sub I, and then now we have 2 things that both equal array sub k. We don't need the second one anymore, so we load whatever is in temp, or what was originally in array sub I, into array sub k. Easy. And so that's that, more or less done. The one caveat with this is this algorithm is very, very slow. And you can see that. As count, if count is 10, Then we have to do this 10 times, and then this loop has to run 9, then 8, then 7, then 6, then 5, then 4, then 3, then 2, then 1. If count is 1,000, this has to run 1,000 times, and this has to run roughly 1,000 times per times that this loop runs. I won't go into the technical language behind how we describe algorithms like this, but suffice to say, you can see that as count gets bigger, this algorithm gets very, very slow. So I'm actually going to ask the user to wait patiently in case they did something, in case they gave us a really big array. So printf, please wait. And then down here at the bottom, before we return from the function, printf, done. Cool. Now we have our bubble sort. Last thing we need to do is print the array to the screen. I've done something like this in the source code that I used for the lectures, and in the examples I did. So let's go through that real quick. All we need to do is run through the array one element at a time and print whatever it is, and print whatever is at the array in that location to the screen. We can do a couple of tricks with the for loop to make it look prettier. So first thing I'm going to do is printf an opening curly brace and a space, and that's all I want. Then for I equals 0, I less than count minus 1 plus I. The reason we're doing count minus 1 here is that I have something special in mind for the last element of the array. For the last element of the array, I want to do the closing curly brace, and I don't want to have a comma after it. So, but for every other value, I can just say %d, comma, space, and pass it array sub I. And then for the last one, I want to printf %d closing curly brace, new line character, array sub I minus, or not sub I, count minus 1. Because remember, there are the last index of this array, the last number that we can use in this subscript operator is count minus 1. Cool. One last little tweak before we compile this. I want to do a kind of before and after thing. So printf before print array printf after. And now let's see if this does the thing we want it to. We have gone a long time without testing this. I highly suspect my code is correct. If it's not, I'll correct the errors in front of you so you can see that process. We are in the correct directory, gcc star.c -o project5.exe. Too few arguments of the function print array. That is because I forgot to call it correctly. 6, yep, here it is. Array num elements. If that was our only problem, then we are doing pretty well. Let's run that again. Excellent. Clear the screen. Project 5. How many numbers do I want to sort? Let's start with 8. Number 1 is going to be 5, 8, 1, 3, 4, 7, 8 again, 6. Cool. And so we can see that my input formatting worked the way I wanted it to. We got the before picture of everything in the order we printed up here. Let's wait, done. Afterward, let's check our work. 1, 3, 4, 5, 6, 7, 8, 8. That looks correct to me. Cool. So this source code will be available on the on the website, I will add that comment I wrote earlier that kind of demonstrates the bubble sort one step at a time. Below here, kind of wrote that on the fly and then deleted it because I forgot the original order. But I'll have the comment here for you to be able to read. You should compare how we wrote this program to see what we did differently. And if you were not able to do this on your own, I hope this was informative. I hope you were able to follow along with me.
Thanks for watching. Please like and share this video.
And understand why all of this works. Thank you for joining us, and I hope you had fun. Hello, welcome to project number 6, the last project in our Intro to C programming. So, the goal for this time around is to convert all of the uppercase letters in a given string to lowercase. This is going to require a little bit of extra knowledge that we didn't really go over in the lecture. Specifically, there is something special about the ASCII character set that you kind of need to know in order to do this. So, I've broken it down into 3 steps here, and am just now realizing I forgot to do the 3rd one, but that's fine because it's very simple. So, step 1, get the string from the user. We're going to be using fgetS for kind of its full purpose here. Step number 2, for each character in the string, if it's capital, then we'll convert it to lowercase. Step number 3, print the result string. Easy. So, this time around, we shouldn't need any helper functions. So we'll just do everything in main then. So, this time, we should be pretty familiar with getting and processing input from the user. So let's just go ahead and do that. Character buffer, do 64 bytes like normal. Format this like that. fgetS, buffer, 64, standard in. This time we're not going to need any conversions though, because we're just dealing with strings and ASCII characters. So, how do we do that? The ASCII character set, which is the default one for C, although strictly speaking, I think modern C compilers can deal with different character encodings. ASCII is just the most common one that they're used to. Anyway, in the ASCII character set, the capital letters of the alphabet, A through Z, are all arranged right next to each other in alphabetical order. I think the value of A in the character set is 65, if I recall correctly. But regardless, the lowercase letters do not come immediately after capital Z, though. There are a few characters between the capital letters and the lowercase letters. And this is by design. In order to convert a capital letter into a lowercase letter, all you have to do is add the ASCII character for a space, which you do just like that, just surrounding an empty space in single quotes. Similarly, you can convert a lowercase letter to a capital letter by subtracting space. So, let's get to that then. We are going to need to iterate over every character in the string. So for equals 0, I less than 64, plus I. If the character is a capital letter, so how do we determine that? So remember that characters are just bytes, which means they're just numbers in memory, and they can be compared as such. So, if buffer sub I is greater than or equal to capital A, and buffer sub I is less than or equal to capital Z, then we know we have a capital letter. So this could be capital A, capital B, capital anything through capital Z. If that's the case, then we know all we have to do is buffer sub I plus equals space. This can look a little weird, but ultimately I find it easier than using the raw numbers in situations like this, specifically because you can have these mnemonics, like just remembering that the difference between capital A and small a is just a space. I find that easier than remembering that it's buffer sub I plus equals 32, which is the ASCII value for a space. If you find it easier to use the raw numbers, then go for it. Personally, I like using the character constants. So, what else do we do here? That ought to be it, actually. Because then all we have to do is printf result cent s character buffer. Yeah, this ought to work. This one is a lot simpler than the last one. Should be a quick breather after the complicated mess that was the last one. So let's go ahead and run through this real quick, just to be safe. Printf, just dump a string to the screen. We have our 64-byte buffer. fgetS will get up to 63 bytes from standard in, making sure the last character is the null character if it needs to. And then for every byte in this buffer, so for every character in the buffer, if what is in that location is anything from capital A to capital Z, we add a space to it, thereby converting it to lowercase. Then we print the result to the screen. Let's compile this and see what happens. GCC star.c-o project6.exe. No output, excellent. String to convert. Let's test this a few different ways. I'm going to test all lowercase first. Actually, I'm going to type actual words that I won't be able to match those up visually. Let's see. Alpha, Bravo, Charlie, Delta, Echo, Foxtrot. Yeah, cool. Looks right to me. Let's try this again. Lorem ipsum dolor sit amet. Converts all of them to lowercase. And now this string is in mixed case. Cool. That seems to work as expected. Yeah, this was a fairly easy, fairly quick little program to run through. If you're still not understanding what's going on here, I recommend looking at a chart of the ASCII character set, or just playing around with this source code at all. Dealing with string manipulation in character sets can be, it takes some getting used to, but once you develop an intuition for it, it'll be smooth as butter. Cool. This was fairly easy. Thank you for joining us.